A hypervisor, also known as a virtual machine monitor, VMM, or virtualizer, acts as a layer of software, firmware, or hardware that constructs and manages virtual machines. The system where a hypervisor operates one or more virtual machines is termed a host machine, while each individual virtual machine is identified as a guest machine. By providing a virtual operating platform to the guest operating systems, the hypervisor oversees the execution of these systems. It is noteworthy that unlike an emulator which mimics entire hardware systems, in the case of a hypervisor, the guest machines predominantly process instructions directly on the native hardware. This setup allows multiple operating systems, like Linux, Windows, and Mac OS, to leverage shared virtualized hardware resources within a single physical x86 machine. In contrast, with operating system-level virtualization, a single kernel is shared among all instances, commonly referred to as containers, although the guest operating systems may vary in user space, such as different distributions of Linux sharing the same kernel. The term hypervisor stems from the concept of a supervisor, traditionally denoting the core of an operating system, where the hypervisor acts as the supervisor overseeing other supervisors. The prefix hyper in hypervisor emphasizes a heightened version of super. Initially introduced around 1970 by IBM, the term was used to describe software that concurrently ran OS 360 and the 7090 emulator on the 360/65 hardware. This term was later applied to the DIAG handler component of CP67. In the earlier CP/CMS system in 1967, the terminology control program was prevalent. While some literature, particularly in microkernel environments, distinguishes between a hypervisor and a virtual machine monitor, VMM, equating these components as constituting the entirety of a system's virtualization stack. In this distinction, the hypervisor embodies kernel space functionality, while the VMM encompasses user space functionality. More specifically, in these environments, a hypervisor denotes a microkernel that implements virtualization infrastructure operating in kernel space due to technical prerequisites, as seen with Intel VMX technology. Microkernels that implement virtualization mechanisms are alternatively termed micro-hypervisors. When looking through the lens of Linux, it's identified that KVM operates as a hypervisor, while QEMU, or cloud hypervisor, serve as VMMs that utilize KVM as the hypervisor technology. Robert P. Goldberg, in his 1973 thesis, Architectural Principles for Virtual Computer Systems, categorized hypervisors into two types. The first type, known as Type 1 or native hypervisors, operates directly on the host's hardware to oversee the hardware and manage guest operating systems. Initially developed by IBM in the 1960s, these hypervisors were the pioneers in the field. Examples of Type 1 hypervisors include Hyper-V, Xen, and VMware ESXi. On the other hand, Type 2 hypervisors, also called hosted hypervisors, run on a typical operating system like any other software. They create a virtual machine monitor as a process on the host system, such as in the case of VirtualBox and VMware Workstation. Interestingly, certain technologies like KVM and BHYV blur the lines between these two types by working as kernel modules that transform the host operating system into a Type 1 hypervisor. The first hypervisors to offer full virtualization were Simon, a testing tool, and the experimental IBM CP40 research system. Operational from January 1967, CP40 eventually evolved into the initial iteration of the IBM CP/CMS operating system. Customized for dynamic address translation on an altered S36040 at the Cambridge Scientific Center, CP40 introduced the crucial capability for virtualization. Unlike previous setups limited to running various user applications concurrently, such as in CTSS and IBM M4444X, CP40 virtualized the hardware's supervisor state. This breakthrough permitted the simultaneous operation of multiple operating systems within distinct virtual machine environments. Programmers later adapted CP40, rebranded as CP67 for the IBM system THARS360-67, marking the introduction of a fully virtualized production computing system. Launched in 1966 by IBM, this system featured innovative page translation table hardware for virtual memory and other advancements enabling comprehensive virtualization of all core tasks, including I/O operations and interrupt management. Contrary to the unsuccessful TSS-360, CP40 and CP67 entered practical use in 1967, with CP/CMS being accessible to IBM clients between 1968 and the early 1970s in source code format, albeit without official support. As part of IBM's strategy to develop robust time-sharing systems for mainframes, CPCMS leveraged hypervisor technology to enhance system resilience and reliability. A resurgence in virtualization technology among Unix, Linux, and other Unix-like operating systems occurred around 2005 due to various factors. These include the enhancement of hardware capabilities, enabling machines to handle multiple tasks simultaneously, the desire to cut costs and streamline server management through server consolidation, the necessity to manage large multiprocessor and cluster installations like server farms and render farms, the benefits of improved security, reliability, and device independence achievable through hypervisor architectures, the capability to run intricate, OS-specific applications across different hardware or OS environments, and the capacity to allocate resources efficiently to accommodate more applications on a host. Major Unix vendors like HP, IBM, SGI, and Sun Microsystems had been offering virtualized hardware even before 2000. These systems were typically high-end, costly setups, though virtualization also existed on certain low and mid-range systems such as IBM P-Series servers, HP Superdome series machines, and Sun Oracle T-Series CoolThread servers. While Solaris was traditionally the only officially supported guest domain OS by Sun, Oracle on their logical domains hypervisor, by late 2006, Linux variants like Ubuntu and Gentoo, FreeBSD, and Wind River carrier-grade Linux could also operate on this hypervisor concurrently, acting as fully virtualized independent guest OSs. Virtualization on SPARC processors was relatively uncomplicated due to Sun's deliberate keeping of the SPARC architecture free of elements that would hinder virtualization, unlike the challenges faced with virtualization on x86 processors. HPE offers HP Integrity Virtual Machines, Integrity VM, to support various operating systems on their Itanium-powered Integrity systems, including HP-UX, Linux, Windows, and OpenVMS. These environments can also function as virtual servers on the Integrity VM platform. The Integrity VM hypervisor layer, hosted by the HP-UX operating system, enables the utilization of multiple HP-UX features. It distinguishes itself from other platforms through capabilities like processor hot swap, memory hot swap, and dynamic kernel updates without necessitating a system reboot. Although the Integrity VM heavily relies on HP-UX, it operates as a hybrid system running on bare metal while executing guest operations. The platform discourages running conventional HP-UX applications due to its unique memory management, scheduling, and I/O policies that are optimized for virtual machines rather than regular applications. HPE also offers VPAR and NPR technologies for stricter partitioning on Integrity and HP 9000 systems, with VPAR providing shared resource partitioning and NPAR delivering complete I/O and processing isolation. The VSE's flexibility has led to its increased adoption in modern deployments. IBM, on the other hand, employs logical partitioning, LPAR technology, on various systems like System 390, Series, P-Series, and IBM S400. The Power Hypervisor, PHYP, on IBM's Power systems acts as a native, bare metal, hypervisor in firmware, ensuring isolation between LPARs. Processors can be allocated to LPARs in a dedicated manner or based on entitlement, where unused capacity can be redistributed to demanding workloads. Multiple shared processor pools, MSPPs, on servers featuring the Power 6 processor allow for collective management of processor capacity among groups of LPARs, permitting dynamic adjustments to capacity allocations. Memory allocation to each LPAR, either at initiation or dynamically, is supervised by the Power Hypervisor, with virtualization capabilities for efficient address control. Input-output I/O adapters can be dedicated to LPARs or shared via the Virtual I/O Server, VIOS appliance partition. The Power Hypervisor ensures high reliability, availability, and serviceability. Supporting hot addition replacement of various components like processors, memory, I/O adapters, and more. Similar advancements are observed in x86 x86-64 server platforms, where open-source projects such as Xen have spearheaded virtualization initiatives through hypervisors based on Linux, Solaris kernels, and custom kernels. These technologies, ranging from enterprise systems to desktop environments, will be elaborated on in the subsequent section. x86 virtualization emerged in the 1990s, initially appearing in box as part of its emulation capabilities. The evolution took a significant step forward in 2005 when Intel introduced VTX Vanderpool and AMD unveiled AMD V Pacifica, embedding hardware virtualization support into their respective x86 processors. An alternative strategy involves adjusting the guest operating system to trigger a system call to the underlying hypervisor instead of running machine I/O instructions simulated by the hypervisor. This method, known as paravirtualization, takes different names like hypercall in Parallels Workstation and diagnose code in IBM VM alongside Xen. Certain microkernels, for instance, Mach and L4, exhibit the flexibility to enable the paravirtualization of guest operating systems. Hardware-assisted virtualization extensions like Intel VTX and AMD V provide several key functionalities. They allow the hypervisor to efficiently manage the execution of guest operating systems by supporting operations such as transitioning between guest and host modes with minimal overhead. This is achieved through the use of features such as extended page tables, EPT, on Intel, or rapid virtualization indexing, RVI, on AMD, which enhance memory management performance for VMs and mitigate the complexity of address translation. Additionally, these extensions permit the safe execution of sensitive instructions that guest operating systems might otherwise execute directly on the hardware, ensuring security and isolation between VMs. Without these extensions, a hypervisor would have to rely on more primitive and less efficient techniques, like binary translation, which increases overhead and decreases performance. Embedded hypervisors, tailored for embedded systems and specific real-time operating system, RTOS environments, differ in design requirements from traditional desktop and enterprise systems by emphasizing robustness, security, and real-time capabilities. Due to the resource constraints common in embedded systems, especially in battery-powered mobile devices, there is a need for small memory footprint and minimal overhead. Unlike the standardized x86 architecture prevalent in PCs, the embedded realm utilizes a broader range of architectures and less uniform environments, with x86, MIPS, ARM, and PowerPC being the commonly deployed ones in medium to high-end embedded systems. Virtualization support in embedded systems necessitates memory protection, user privilege distinction, ruling out most microcontrollers in the process. Manufacturers of embedded systems typically possess their operating system source code, reducing the demand for full virtualization. Instead, the performance benefits of paravirtualization often make it the preferred virtualization approach in this domain. However, recent developments have seen ARM and MIPS incorporating full virtualization support as an IP option in their latest high-end processors, such as the ARM Cortex-A15 MP core and ARM v8 EL2 architectures. Variances between virtualization in server desktop settings and embedded environments encompass the need for effective resource sharing among virtual machines, low-latency inter-VM communication, comprehensive scheduling and power management oversight, and precise control over data flows. System virtual machines, known as full virtualization VMs or SysVMs, act as a substitute for real machines by enabling the execution of complete operating systems. A hypervisor facilitates this by utilizing native execution to effectively manage and allocate hardware resources. This enables the creation of multiple isolated environments on a single physical machine. In modern systems, hypervisors leverage hardware-assisted virtualization, utilizing specific features in the host CPUs to aid in virtualization processes. On the other hand, process virtual machines are tailored to run computer programs in a platform-independent setting. Certain virtual machine emulators like QEMU and video game console emulators go a step further by emulating diverse system architectures. This emulation capability allows these virtual machines to run software applications and operating systems intended for different CPUs or architectures. Additionally, OS-level virtualization permits the partitioning of a computer's resources through the kernel. It is important to note that while these terms are related, they are not always used interchangeably. Virtual machines, as originally defined by Popek and Goldberg, serve as isolated duplicates of real computer machines. Presently, virtual machines are not constrained by direct emulation of physical hardware. The hardware running the virtual machine is typically denoted as the host, while the emulated machine itself is termed the guest. One host machine can support multiple guests, facilitating the emulation of various operating systems and hardware platforms. The concept of virtual machines initially arose to enable the simultaneous execution of multiple operating systems, promoting efficient time-sharing capabilities among single-tasking systems. System virtual machines represent an extension of the historical concept of virtual memory, exemplified by IBM's CP/CMS, the pioneering system supporting full virtualization. Unlike virtual memory systems, system virtual machines allow users to incorporate privileged instructions within their code, offering benefits like incorporating additional input on output devices not typically permissible by standard systems. The continual advancement of technology in virtual memory and virtualization has led to innovative approaches such as memory over commitment systems, managing memory allocation efficiently across multiple virtual machines on a single operating system. Techniques like kernel same-page merging, KSM, can consolidate memory pages with identical content, optimizing resources among virtual machines running on the same physical hardware. A process virtual machine, also known as an application virtual machine or managed runtime environment, MRE, operates within a host operating system like a regular application and is dedicated to supporting a single process. This virtual machine is generated upon the initiation of a process and terminated upon its closure. Its primary function is to establish a platform-independent development environment that conceals the intricacies of the underlying hardware or operating system, enabling a program to run consistently across various platforms. Process VMs offer a high-level abstraction, focusing on a high-level programming language instead of the low-level instruction set architecture ISA abstraction that system VMs provide. These VMs are carried out using an interpreter with performance levels comparable to compiled programming languages, attainable through just-in-time compilation. The prevalence of this type of virtual machine has notably increased within the realm of the Java programming language, leveraging the Java virtual machine for its implementation. Additional instances include the Parrot virtual machine and the .NET framework, which utilizes the Common Language Runtime as its VM, serving as an intermediary layer for any computer language. A distinct variant of process VMs caters to systems that oversimplify the communication mechanisms within a potentially diverse computer cluster. This specialized VM model involves multiple processes, one for each physical machine in the cluster, aiming to simplify the development of concurrent applications by allowing programmers to concentrate on algorithms rather than the intricacies of communication mechanisms offered by the interconnect and the operating system. Unlike standard process VMs, these systems do not focus on a particular programming language, but are integrated into an existing language, commonly providing support for multiple languages like C and Fortran. Examples of such systems encompass Parallel Virtual Machine, PVM, and Message Passing Interface, MPI. Sun Microsystems, now Oracle, incorporated similar features in their UltraSpark T-Series processors in 2005. Platforms like KVM, VMware Workstation, and Zen adapted to this hardware. OS-level virtualization virtualizes a physical server at the OS level, allowing multiple isolated servers to operate on one physical server. The operating system environments share the same kernel as the host system, with implementations like FreeBSD jails, Docker, and Solaris containers. Virtual machines commonly utilize virtual disks for storage, where a virtual hard disk is typically simulated as a file matching its capacity. The process involves transparently translating the virtual machine's disk operations into actions on the corresponding file. With this translation layer in place, operations can be intercepted and redirected to different files based on specified criteria. Each snapshot generates a new file functioning as an overlay for previous ones. Data is written to the most recent overlay, while reading existing data requires scanning the overlay hierarchy to access the latest version. Consequently, the stack of snapshots effectively creates a unified disk, resembling the concept of incremental backups. Additionally, snapshots may encompass other virtual machine elements such as RAM contents, BIOS settings, or configuration details. The concept of save state in video game console emulators mirrors the functionality of these snapshots. Restoring a snapshot involves discarding subsequent overlay layers, rerouting all new changes to a fresh overlay for continued operations. The process of moving the snapshots to a different host machine along with its respective hypervisor involves temporarily stopping the VM, creating a snapshot, transferring it to the new host, and then resuming operations on the new host, which is commonly referred to as migration. By keeping the older snapshots in sync on a regular basis, this operation can be executed swiftly, allowing the VM to offer uninterrupted service, even when its original host is undergoing maintenance or any other relevant procedures. Failover, a concept similar to migration, enables the VM to sustain its operations in the event of a host failure. Unlike migration, failover permits the VM to continue from its last coherent state, provided by the backup server, rather than its immediate state. This approach ensures operational continuity under unfavorable circumstances. Nested virtualization is the practice of running a virtual machine within another virtual machine, with the flexibility to continue this nesting to multiple levels. This concept encompasses scenarios where one or multiple hypervisors operate inside another hypervisor. It's worth noting that the internal virtual machine does not have to match its host virtual machine in type. For instance, you can run application virtualization within a virtual machine created through hardware virtualization. The demand for nested virtualization grows due to mainstream operating systems incorporating hypervisor features. Utilizing these features in a virtual environment necessitates nested virtualization support in the overarching hypervisor. An illustration of this is how Windows 7 can execute Windows XP applications within an internal virtual machine. Additionally, transitioning existing virtualized setups to a cloud infrastructure under the Infrastructure as a Service (IaaS) model proves complex without nested virtualization support in the target IaaS platform. Implementation of nested virtualization on a specific computer architecture hinges on the presence of supported hardware-assisted virtualization features. In instances where the architecture lacks the necessary hardware backing for nested virtualization, assorted software methodologies are leveraged to enable this functionality. As time progresses, more architectures are adopting the fundamental hardware support. For instance, starting from the Haswell microarchitecture introduction in 2013, Intel began integrating VMCS shadowing as an acceleration technology for nested virtualization. Significant advancements in virtual machine VM technology are expected over the coming years, transforming how they are used and integrated into computing environments. One key development is the evolution of lightweight virtualization through enhanced micro-VMs, which are expected to offer faster boot times and reduced resource usage compared to traditional VMs while maintaining isolation and improved performance. This advancement will cater to edge computing needs, allowing for more efficient management of resources across distributed networks. Another anticipated evolution is in the realm of serverless computing, where more sophisticated VM orchestration will enable serverless platforms to auto-scale workloads more effectively with minimal configuration. Quantum VMs are also expected to emerge as research in quantum computing progresses. These specialized VMs will simulate quantum environments, helping developers transition their applications to quantum systems once they become commercially viable. Furthermore, the focus on sustainability will drive the development of energy-efficient VM solutions. The use of VMs will likely evolve to support more complex and hybrid cloud architectures, bridging on-premises infrastructure with cloud resources and catering to the increasing demand for hybrid and multi-cloud strategies.